All right. Okay. Hello, everyone. Yep. So today we will be discussing about a topic which I know a lot of people are struggling on for IGCSE Maths 0580 Extended. Today we will be discussing about vectors. Right. So a vector is essentially just a line which has a length, a magnitude, and a direction. Right. The direction of a vector really matters because say we have a vector v1 like so, and then we have another vector like this, and let's call this v2 like so. Even though the length, the magnitude of v1 and the magnitude of v2 are the same, the direction is not the same, and that means that the vectors are not equal. The vector have different directions, so we cannot say whether they are the same or they are different, right? So I'm going to begin with a little example, right? That say for example I have a vector like this. Well, if this is A, then the same vector, same magnitude in the opposite direction is minus A. The same vector in the same direction, which has half the magnitude, is half of A. Right. Note that all three of these vectors have the same direction, so it is alright to compare them in terms of their magnitude only. Note also that if the direction is opposite, then the vector is negative. If the direction is positive, then the vector is positive. And also, if we think about it, then a vector like this, where there is another vector in the same direction, is essentially the vector itself multiplied by a constant coefficient. Let's call this constant coefficient k. Then in that case, then basically every vector which has the same direction as the original vector is basically the scalar multiple of the vector itself, because as you can see, the value of A never changed. We are only playing around with how much of the magnitude of A we are covering for the distance, right? Now moving on, right? I'm going to now discuss how we can do operations on basic vectors, right? So the whole idea is like this. If we have a vector OA like that, and then we have a vector OB, and say this is A, say this is B, then the vector OB, which connects O to B, is basically you are walking the route from O to A, then A to B. And so this is really just A plus B. Why is it A plus B? Because your starting point and your end point remain the same, no matter what. So in other words, you can just add the vectors together if the route you're using has the same starting point and the same end point. Right. Say now we have a point C, and then C connects to B like this. Then we can of course write that OC plus CB equal to OB, because you can add the vectors together, and this has to be equal to the value given for OB, which is A plus B, right? Another way to add vectors, this is a very important method, especially if you're taking physics right now, right? This is what's called parallelogram method. So say we have a point O, a point A, a point B. So this is the vector A, this is the vector B. Right. If we connect a line from A extending so that this line is parallel to OB, and then from B extending so it's parallel to OA, and as you can see, this meets all the basic features of a parallelogram, geometrically speaking. Well, then let's say this is the point C, and then the vector OC is actually just the addition of the two vectors forming the parallelogram. And this is easily proven by the fact that, by the way, this is also something you have to know. If two vectors are parallel, then their direction is the same. And since we know that lengths OA and BC are the same, so this is just A. And by addition of vectors, you can clearly see that this is A plus B. Alright. Okay, so moving on, now we will consider another idea about vectors, in that if you have, this is O, this point right here is A, and this point right here is B. Yeah. Again, because they are the same direction. Yes, and this plays right back into the idea of the magnitude of the direction of how big the vector is. We can say that if this is A, if OA is A, then OB can be written as a constant, let's call the constant K times A. Then this is basically just K minus 1 times A. Why does this work? Because all the points are collinear. And if the points are collinear, then we can express the vectors in terms of, again, scalar multiples of 100, right? Yeah. And really, that also means that using that idea, we can actually divide a vector in half. We can turn the direction of a vector upside down and we do all this to find the vector that we want to find as stated in the question. Right, here's a simple example. Say we have something like this. Right, so this is O, this is A, this is B, this is C. Well, yeah, so, and we're given that OA is A, OB is B. Well, and we want to find OC. Well, how do we find OC? OC can be found by, if you think about it, you can find this, right? And then let's say AC to CB is 3, 2, 1. From there, you can find AC because AC is just 3/4 of the full length of AB. And then from there, you can add these vectors together. But the question is, how do we find AB? We have OA, we have OB, but there is no direct route from A to B. Here's the trick. We can think, if we think OA is the vector A, then we can also say that AO is the vector minus A, which means that AB is just B minus A. If AB, right, because this is A minus A plus B. If AB is B minus A, then AC is just 3/4 of the way through. And then you would want to add that to your original OA. And that gives you 1/4 of A plus 3/4 of B. And basically this is the whole basic idea behind the geometric manipulation of a 2D vector in mathematics, in that you can basically just flip your vector around and divide your vector into multiple parts to find the section of the vector you really want. Okay. Okay, moving on. Yep. Now I'm going to discuss some slightly more advanced stuff. Right. This applies to both normal math, and actually in some way this applies to a bit of A math. Yeah. Right. Okay, I'm going to begin with with the idea of say this is O, this is the origin, and then this is A. Right, so let's call this vector A. Then we can say that A is the position vector of the point A from the origin O. Why is it the position vector of A? Because it's the position, it's the total vector length covered by that A from the origin. And really, if we have something like this, let's say, let's call this guy X, and so now we have a vector X like so. This vector X is the position vector of X from the origin O. Right. For moral math, all you need to know is basically just how to find the vector, whether they want you to find a specific vector or they want you to find the vector from the origin, the position vector, based on how the geometry of the shape given to you looks like. Right. For this type of question, it is very much essential that you know how to add your vectors together, you know how to get from one point to another via the route, and if the vector that you need is in the opposite direction, you just add a minus sign. Now I'm going to go discuss a slightly more advanced variation of this type of problem. Right. This is the review on vectors from Miss Naturally. 5b. Well, so what do they want? A P, C, P, O, P, and we're given that OP and AB are extended to meet at Q. OP and AB extended to meet at Q, which means that if you draw the diagram, it should look like this. And this guy right here is your Q. Alright, so what do they want? They want a C, C, P, O, P, and the position vector of Q, which means they want O, Q. Right, so they want, so now we know that they want you to find AC, CP, OP, OQ. AC, CP, OP, and OQ. AC is this is basically the flipping of the direction idea that I told you about, because AC is just, if you think about it based on the route, it's AO plus OC, right? Well, what's AO? It's just the opposite. It's just OA but flipped. So AC is C minus A. What is CP? Well, so we know that C is C minus A. What is CP? CP is basically just CP is just 3/4 of CB, right? What is C? And we know CB is parallel to OA, and that means that this is just 3/4 of A, right? And then how do you find OP? OP is just right. OP is just 3/4 of A, which is CP, plus your OC, which is your C, and that's your OP, right? Okay, so if we now if we want to think about it, so now if we want to think about it, right? So if we want to think about it, right, so we can now find OQ by considering how it extends from OP, right? Yeah. At this point, there are two ways you can basically kind of do this, right? Well, yeah, well, the first way is really similar triangles, because if you know that is 1/4, then PQ by similarity, right? Yeah, this is basically the same. PQ is basically 1/3 of OP. I already know OP, so PQ would then be equal to 1/4 of A plus 1/3 of C. And OQ is then just OP plus PQ, which gives A plus 4/3C. Yep. Yes. Again, this works because again of the scalar multiple thing that I discussed. That if you extend a vector, then you're just extending the magnitude. You're not changing direction. Right? In a way, that also leads us to be able to get some kind of method to find this by thinking of it as two different scalar multiples of the same vector. Yeah. And basically, because the scalar multiples are the same, so you can equate them and you will get a set of simultaneous equations which you can solve, and then the solutions you can substitute back into your vector, and from there you can find your expressions for the entire vector itself. Yeah, this is called the scalar equation method, and this is the method that will be tested in additional math 0606. It's slightly more advanced, but I think that this would be something that I need to explain a bit about, because I think that, especially because this is what is going to be used, especially in JC1, JC2. So basically, how it works is that we let OQ be just a constant multiple of OP, which we already know. Let's call it K. And then we know that AB is extended to Q. So AQ, let's say, is a scalar multiple of AB. Basically AB times something, right? Let's call it J times AB. In the real exam, they don't have to use the constants K and J. They can use M, they can use N, they can use oftentimes Greek letters, maybe most of the time lambda and mu, and they can use any other type of constant that they want. But essentially, the method is this. We know that OQ is K times OP. What is OP? OP is 3/4 times 3/4 times A plus C. And here's the thing, because we multiply everything by a constant multiple, so basically we add a K onto all the vector components, onto A, onto C, right? So that's your OQ. Your AQ is what? AQ is J times AB, which is J times C, and that is AQ. OQ, but we're not done yet. That's AQ. OQ is OA plus AQ, that means JC, which means that if we equate the vectors, then we get that 3/4 times K equals 1, and J and K equals J. And this gives you K is for 3 times. K is for 3. What happens if K is for 3? Then J is also 4/3. And so we can say that OQ is, and we get the same answer also. Yes, this is the other method. This is the slightly more advanced method that I think you should know. And of course, you can use both methods. Cambridge is going to mark both of them. Right. Now I'm going to continue with an application of vectors that you will also see in in 0580. Well, all of the vector type questions will be either the geometric type, just like the one we discussed earlier, and the other one is a combination of vectors with the idea of for geometry. basically the whole idea of this type of question is that it's is that the vector is essentially the position vector from origin O. So let's take this example. P is 2, 3. Right. Then if this is the position vector from O, then if we have point P and OP is the vector P, then P is 2, 3. Again, always X first on the top, then Y at the bottom. Yep. And this is also something that you will need to understand for translation in transformation, because you'll need to understand how this type of vector, what we call column vector, you will need to understand how this type of vector works to be able to answer the transformation type question properly. Right. Okay. Right. The magnitude of a column vector is basically just the x squared plus the y squared and then you square root it. Why? Because if you think about it, this is just the vector 2, 3. And so if we think about it as 2 points on a coordinate plane, then if this is 0, 0, then you translate that point by the vector 2, 3, then you get 2, 3. Yep. And basically the magnitude is just finding the this line, which is obviously the root of 2 squared plus 3 squared. Yep. And that is how you would find the magnitude of a column vector. If you are given a type of vector, if you're given a column vector with 1 point given, like this for example, basically you just have to think of like this. Right, this is because this is A, right? Basically you just have to think like this. This is A, right? This is B. And so you just think of it as a translation by x units and y units. So the x units of -4 and then the y units of 6. So, and in that case, by reversing the translation, we can also say that it's 6, 1. For this type of question, oftentimes they will combine it with for geometry actually. And this is a type of question that we can often see in both normal math and A math. Yeah, this is a topic that's common to both. Right. So I'm just going to discuss part 4 here. Right. The whole idea right, is we know that a is minus 8 comma 8. Yeah. Again, you can just think of this as a translation. And yeah, so this is x and this is y, right? So basically, to find the to find the parts of e, you just need to translate the x coordinate by 4, which means you add 4, and then the 8 you just add by minus 7. And this allows you to clearly see that it's x then y, right? Yeah. Okay, and this connects really well to another topic that often comes up in math, which is, of course, transformation. Transformation in this case being the transformation of translation. And in a way, it's just your moving all of the points of the shape by the amount of x and the amount of y that they ask. Last of all, before we wrap things up, I want to end this with one final trick that is really going to help everyone here. Basically, if you're confused on how to find the vector, say something like this. Well, you want to go from here, right? You want to go from here to here. Well, just think of it as you're at school. You want to walk to your home, and you just and you have to follow all the roads that are straight, and you can't cut through any shortcuts. And that's basically how you can think for all the vector questions out there, right? And with that, this session is over. Wish you all the best of luck for tomorrow, and don't forget to study. And remember, guys, we can all get A star for maths. We can all do this. Okay, thank you for coming to this session, and I hope that you will be able to answer these types of vector questions on tomorrow's IGCSE.